Welcome all again. Thank you very much for being here. Please take a seat. We are going to start the next session. In this case, a technical session from this day, from practical experiences from data formats to AI. So I welcome Federico Lecumberry as moderator. Thank you.
Hello. Thank you very much, Andres, and everybody for organizing this awesome fourth meeting of LABI. So in the first session in the morning, we assume we have our data in our servers, we have computer power, we have everything to work with data. Now in this session, we're gonna see some examples on how data analysis, data processing, AI is done in the region for obtaining more information and for have some connection with the clinical information of the physicians, for the physicians. So we have three different speakers. We have Andrea from Guatemala, Enzo from Argentina, and Rosana from Brazil, and they're going to talk us about some of these projects. The order is, I choose this order because first with Natalia, sorry. First with Andrea. Andrea's going to talk us about Natalia, an AI system for helping the midwives for pregnant women in how to train to do ultrasound analysis in pregnant women. Then we're going to switch to Enzo. He's going to talk about CheckMax, a system for building and testing a large-scale data set of automatic anatomical segmentation for chest X-ray images. And then we're going to end with Rosana, who's going to talk us about the pipeline that they developed for an AI tool for lung evaluation and how they put this system in the hospitals, in some of the hospitals in Brazil, and how they extract information for the physician in order to take, to generate more deeply informative analysis and diagnosis. So we're going to start with Andrea Lara. She's from Universidad Galileo in Guatemala. Andrea Lara holds a PhD in biomedical engineering from Graz University of Technology in Austria, a master's degree in biomedical engineering from the University of Lübeck, Germany, and a bachelor degree in electronic engineering from Universidad Galileo. She's the founder and director of the first academic program and research laboratory in biomedical engineering in Guatemala, and currently serves as director of the Biomedical Engineering Institute at Universidad Galileo. Her research focuses on artificial intelligence for medical image analysis and the development of technological solutions that address local healthcare needs and challenges. So please, Andrea, thank you very much.
Okay. So, good morning, and first of all, I want to thank for the invitation. I'm more on the medical field, but anyway, I'm learning a lot, so thank you very much for the invitation to LABI. And today, I'm going to share our experience on this project titled Natalia, and some of the lessons that we have learned during the process of developing this tool. So first of all, let me give you an overview of what's the situation in Guatemala. So on one side, we have the patients that are in rural areas, and on the other side, we have the specialists that are usually on urban areas. And specifically in Guatemala, that means Guatemala City. Yeah. So as you can imagine, these pregnant women do not have access to specialized services because of different barriers. So there is, of course, traveling, but also budget or cultural or even linguistic barriers. However, they're not completely alone. There is an important figure that is the midwives. So the midwife is trained to provide a basic prenatal care. However, she's not trained to perform specialized studies like, for example, ultrasound. And that's where our system comes in. So our system is called Natalia, and the idea of this project is to allow midwives to perform ultrasound studies by using AI. So the idea is that we are going to provide the midwives with portable ultrasounds, then they can perform the ultrasound studies using a protocol that is known as blind sweeps that doesn't require as much training as a person that performs ultrasounds does. So the idea is that they only follow like a specific trajectory over the belly of the pregnant woman. And then the AI is used to analyze the videos, and these videos, it will contain relevant information like fetal planes. And here the specialist can perform some biometry and also identify if there are some problems with the baby. So then the AI analyzes these videos, gets the images, and then all these images are reviewed by the specialist. And this can be performed in an asynchronous way, so it doesn't have to be connected all the time. And then he can provide an feedback, like a report of all the analysis, give it back to the midwife, and then she can give this information to the patient. So the idea is to connect them and allowing to have access to these specialized studies, like the ultrasound, because as we know, these are relevant and really necessary during the prenatal stage. So I want to highlight key components of this project. The first is that since this project is aimed for the midwives, we're working in close collaboration with them. So they are part of the whole process that I'm going to present later. Then, as I mentioned, we are using the blind sweeps. So the idea is, again, that they don't have to go through a specialized training. They only have to follow some trajectory, like this. And another key important access is that we have a human in the loop. So the idea is not to have AI to automate the diagnostics process, but to have a specialist that is going to really review all this information, that the AI is only detecting what is relevant from the whole study. And this is really important because there might be some conditions that might not be so common, so the AI might miss them, and that's why we need the specialist in the loop. So now let's go through the experience. So we have performed so far 2 studies. One was a proof of concept, so we want to test the whole workflow on really controlled conditions. And the other is the feasibility study that this is still ongoing. So for the proof of concept, what we did is that, we want to test the whole workflow that I just presented. So we want to test the blind sweep, we want to test the AI capability to identify the planes. And then the most important, we want to test how this is perceived by the midwives and how they feel about it, if it's too difficult to use or not, because that will influence in the adoption. So, in this case, I am just going to give you an overview of our experience. And to develop AI, we need data. And this data has to be standardized to be helpful to train the models. And here we try again to do it the most controlled way. So for that, we started with a phantom of a 23 weeks pregnancy. And it has a fetus like the one you can observe over there. And then we learn a few things that I want to share. And the first one is that when you use portable devices, what it does is that it records the screen. So if you're using a phone, it's going to look like there in the corner. And if you use a tablet, then you have a bigger size. Okay, the problem is that when you download these videos, they're gonna be like the size of the device. So this is gonna give some problems when you want to train the model, because you might miss some information because of the resolution of the image. And the other thing that is important is here that we have studies that has around 1,600 frames, so a lot of frames. But since we're using blind sweeps, there are a lot of frames that are not relevant. So they don't contain the heart, the abdomen, they only contain background. So we have to clean this data, process the data, and this is really, really important because we will have an unbalanced data set, but more of that because we have to go to the next step, that is annotation. So we need a specialist to review these studies and analyze where the fetal plane is present. So imagine that if you have to go, I don't know, if we have 10 studies plus the 1,600 frames, It's going to be a lot. Even for me, it's going to be a lot. So the idea is that we want to clean this data, and then we want them to identify what are the optimal planes. However, here there was another experience that we learned. And we are working with radiologists and obstetricians. And they have different parameters to decide which is the optimal frame. So one really important thing to do before starting with annotation was to create an annotation guideline to really define what is the optimal, for example, for measuring the head or for measuring the abdomen and so on. And the other thing is that since we're working with the specialists, you have to keep in mind that they're busy because they are obstetricians and they are radiologists. So that might be some shift in the timeline that you define for the annotation. And this is just something that you have to keep in mind. And also how you're going to ensure that they're going to be committed to them. Because during the process, we lost at least 2 of them. So they were not longer annotating. And then it was, okay, now we have the data, we train the system, and we train different algorithms. And then the other important thing is not just developing the AI that works, but also test it. And we want to test it with the users. So for that, we also have to build an architecture that uses this AI that we already trained, and then give it to the midwives to test it so they can upload the studies, and then this AI can detect the planes and give it to the expert and give the feedback. And once is all that built, then we do what is important to test how this is perceived by the midwives, so how they feel. And this is the whole process. It's not only the AI tool, but also the protocol acquisition. How easy, how difficult it was for them to perform these blind sweeps, because this will really influence in the adoption of the tool. So this is something that we already test, and here is a paper where we share our experience. And just to finish, now we're going through a feasibility study, so now we move from more uncontrolled conditions, so we're working with real patients. And here, where we are is that we're collating data, and the most important thing is, since we are now working with real patients, what is really important to mention that some other steps are added, like for example, anonymization of the data, really important, but more important from that is participant recruitment and consent, and then how we're going to handle this information. And for this part, the consent and the recruitment, we learn a few lessons. So the first is that Guatemala is a really multilinguistic country. We speak 22 Mayan languages plus another 3. And sadly, we have a high illiteracy rates. So that means that for recruitment and for getting the consent, in most cases, we need a translator to explain what we are going to do with this tool and with the whole study. And also figures, because in some cases they cannot read. So how to clearly explain the whole process. Then it's really important that you define your data pipeline planning. So how you're going to collect the data, how you're going to save it, and all that. Of course, the annotation. The most important is how you're going to ensure the expert involvement, because in our experience, that has been really difficult. So just to keep in mind. And finally, I think the most important is that we learned that this tool has an impact. So during the process, we have been, for the feasibility study, we have been working with patients. So far, we did 40 studies. And from those 40, we identified 4 high-risk pregnancies. So that really tells us that this tool can have an impact on lives. In this case, we're 8 lives. So that is something to keep in mind, and this is our main motivation about this project. And with that, I just want to thank the collaborators and the funding agencies, and of course, our team. So thank you very much.
Thank you, Andrea. Thank you very much for the talk. We have time for one quick question and a quicker answer. That's my question. The question is the question are at the end. Sorry. Thank you, Andres. Next. I'm going to ask Enzo to come to the scenario. I'm going to introduce Enzo. Enzo Ferrante, exactly. Enzo holds a PhD in computer science from Université Paris-Saclay and an INRIA and a system engineering degree from UNICEN University here in Argentina. And he was a postdoctoral researcher at Imperial College London, a Fulbright visiting researcher at Harvard Medical School, and invited professor at Université Paris-Saclay. Currently, he's a faculty researcher at the Institute of Computer Science here in this faculty, in this campus. He's a researcher at the Laboratory of Applied Artificial Intelligence, and it focuses on machine learning for computer vision and natural language processing, with an emphasis on fairness and robustness in healthcare applications. His contributions to the field have been recognized with distinctions such as the Mercosur Science and Technology Award, the Google Award for Inclusion Research, and the UK Royal Academy of Engineering Distinguished International Associate Award, among others, of course. Enzo, everything's yours. Thank you very much.
Just going to put a timer here. Because,
yep.
Yeah, cool. Yes, this is... Okay, cool. Hi, everyone. Thank you very much for the invitation. I'm really happy to be here, which is kind of at home, because I'm on the other side there. And yeah, I mean, I'm going to be sharing something that is kind of related to what Andrea was presenting, in the sense that these are more like macroscopic images. Like, I know this is LAVI, this is more bioimaging, and you have been discussing a lot about microscopy and these kind of things. But here we will be talking about X-ray. And actually, it's not really the data set that I'm going to present here, what I'm going to share, but maybe the journey we had when we created this data set. And what were the challenges that we encountered when creating a large-scale data set of annotations, which is different from creating a large-scale data set from images. And this is where the emphasis of the talk is going to be. So we know in the machine learning community, and especially nowadays in the era of foundational models, that we need data to train our models. Without data, we are nothing. We cannot train that. So it's really important to have big data sets, and they can come in different ways, like maybe because of a challenge that someone organized. In those cases, you have a lot of labels usually associated with the data set, but also sometimes associated to papers. Like, data sets are composed of different parts, and here in this talk, we are going to be interested particularly there, on the labels. Because capturing the images is one thing, but giving semantic to the data set implies adding labels there. So what I'm going to present now is CheckMask, which is a data set we create by taking all the large data sets of X-ray images that were out there, or many of them at least, and creating annotations for them, and trying to validate these annotations at large scale, which I believe is something very important when we think about data sets. So this is the paper, in case you then want to go and check it. But basically what the data set is about is, we have X-ray images. I don't know if this is, yeah. We have X-ray images in the dataset, and what we created were annotations for segmentation of organs. That's a problem I've been working for many years already. So we are trying to segment organs of interest for the doctors. In case of bioimages, maybe you were, I don't know, trying to segment cells or something like that. Here, what we developed was a method that allows us to create this segmentation mask. And as I'm going to show it here now, it was very robust when we were developing this method. So we say, hey, people are needing labels. We need segmentation masks for different tasks in medical image computing, for predicting different diseases, for annotating organs, for understanding how shapes of organs change with certain pathologies. So basically, here we created this data set that is composed of more than 600,000 images with the corresponding annotation that we generated. These annotations, I'm not going to enter a lot into details here. There are many technical details I'm going to leave outside, but basically here, these are represented as graphs with correspondences. And the nice thing is that you can have like exactly labeled the same part of the lung across different patients, so you can perform kind of inter-patient analysis. And here comes the important thing for this talk. That is, we wanted to release the dataset not only with the automatic annotations, but also with some metric that tells how good the annotation is. I think that's a very important value of a dataset like this. And I'm going to tell you a little bit of the issues we encountered there. This was also validated by humans that annotated a few images, but we cannot ask humans to annotate 600,000 images because otherwise we just release these annotations and that's all, right? So a little bit of the story here goes on how we did to do that and also to perform some kind of fairness analysis. I'm going to leave that for the end in case I have time, which I don't think. To tell you a little bit about this idea of fairness and why is that important in this type of data sets when you are performing the analysis. So just to quickly go there, first part of the journey started with data preparation. So what we did, it was to take 5 of these large-scale data sets of images that were already out there, published by different universities, hospitals. We did some kind of filtering and we ended up with more than 600,000 images. We had the images, so we had to standardize them, of course. This is a very challenging task. When you are dealing with multi-centric data, you need to standardize that data so that it can be processed by a deep learning model, right? And that's what we did there. Many challenges appeared there. We also assessed the existence of metadata, which is another very important tag when it comes to data sets. Not only the labels, the segmentations, but also knowing who were the people from which these images came from. Not the name, not the address, but maybe sex, maybe age, maybe ethnicity, things that then can help us to perform this fairness analysis that I was mentioning, that I will mention at the end. And something that was very important and that we usually neglect, and these licenses and terms of use of the dataset. We were building labels for datasets that were already there. Maybe some of you have done that as well with bioimages. Now, were we allowed to do that? We didn't know if we were allowed to publish the labels because these are things that we are creating that are derived from the original images. And actually, until I submitted the paper to the journal, I didn't realize that I had to ask to the original authors about that. And that's what we did. Unfortunately, it went well. Everyone say, yeah, you can go ahead. Some of them say, yeah, you can go ahead, but it would have been nice if you had asked before doing that. And this is maybe one of the lessons that I learned with this journey of creating data sets that are annotations derived from images. Be careful with the data you are using for creating that, because maybe they don't allow you to share it after. And we were in kind of an open data initiative here. We wanted to share that for people to use. Okay, that was the preparation part of the data, if you want. Then it came the processing. Andrea was mentioning some deep learning architectures they use. We used our own. Here is where most of the work was with some of my PhD students. I'm not going to get into the details of that, but basically it's an architecture that takes an image, goes through standard convolutions, graph convolutions, and build the organ that you want to segment. And the method is very robust. If you compare with, this is what we usually do in medical imaging computers, just showing that our model is better than other models for different type of problems that you can encounter when generating these images. This is the paper in case you want to get into the details of the method itself. But again, it's not there where the main, I think, story goes for this talk. Here, I wanted to center in this other challenge that we had. That was, okay, we have the images, we created the labels, people are going to use these labels for making predictions or whatever. How can we tell them how good are these segmentations if we actually don't have the ground truth for saying that? So we took like a kind of mixed approach that I think is nice sharing, that was mixing human experts with automated methods for quality checking. And the first thing we did to validate was to say, okay, let's take a sample of the images, and we contacted researchers and radiologists from Hospital Italiano de Buenos Aires who helped us annotate a few of them. So there we had like the first validation. For a small sample of 150 images, we had human, oh my gosh, we had annotations. That was one thing. We validated, everything was fine. The second thing was to create automatic annotations and automatic metrics, sorry for that. And that I can unfortunately, due to time constraints, not go into the details. If you are curious about that, we can discuss how we did that. But basically it's a way to estimate quality metrics without having ground truth for this type of issues, for this type of problems. And I think that's a nice story. There are methods that you can use when you are creating automatic annotations for estimating the quality of these annotations without having any ground truth. And I think that's important if you are thinking about creating data sets. Try to leverage these methods and use them to provide these estimates. They correlate very well, actually. This is the estimated metric, this is the real metric. They correlate very well with the quality, so they were useful for that. Actually, by using them, we looked at which were the images that we were segmenting that had the lowest values for these indicators, and we found that these data sets, these large-scale data sets, had garbage inside. Had, for example, images of cell phones, and they were tagged to be X-ray images, chest X-ray images. That was discovered thanks to these kind of methods. Now, the third thing we did, which I think is also a very nice idea for validating the quality of the annotations you create, was to do what is called like reverse classification. We basically took these annotations, trained models, and measured the quality of these models on data for which we had annotations. That helps you to understand if my annotations are of good quality, then they can be used to train a model that will be good. So it's like using the annotations in the inverse way. And I think that's a very smart trick that you can also use when you are creating these type of data sets. This worked pretty well actually for us. And just to conclude this kind of story, there was an issue that I left for the end, but I maybe use 1 minute more here. That it's something that maybe you can also take as a take-home message or something to learn. Many years, well, not many years, 5 years ago, we published this paper in PNAS where we show that actually these models that we use for classification based on X-ray can be biased. And what it means to be biased is that the model may have a very, very different performance in one subgroup than in another subgroup. That means, for example, the model can underperform in women when compared to men, in young adults when compared to young people. This was a pretty disruptive paper for our field. And since then, so many other papers came out. They showed actually that segmentation models can also be biased with respect to different ethnicities. So we came here and said, hey, is our data set biased somehow? Can we understand whether the data set is biased, whether the quality of the annotations we are creating is lower for one group than for the other without having ground truth? Because if you have ground truth, that's easy. You can estimate any kind of metric based on the ground truth. What happens when you don't have ground truth? Well, it turned out, and if you are curious, you can check our other paper there, that you can do that. You can understand biases or try to do what we call unsupervised bias discovery, that is looking for biases even when you don't have labels. So there is no excuse to don't look for biases. Even if you don't have labels, there are ways to do that. And actually what we found that was pretty interesting, and with this I conclude, is that when I was looking at the images, so you know that X-ray images can be antero-posterior or posterior-anterior. That depends on where the acquisition machine is taking the image. And what we found is that anterior-posterior images had a much lower performance than posterior-anterior. And that, when we talk to our radiologists, they say, yeah, that makes complete sense. Because anterior-posterior images come from hospitalized patients. Hospitalized patients usually have tubes, have stuff on top of them, which degrade the quality of the image, what makes the segmentation problem much more complex. And so we found this kind of bias there, which was confirmed by the radiologist using our unsupervised bias discovery method, that if you're interested in, we can discuss. Also, younger patients were presenting lower performance than older patients. That's a little bit of the story. So this was the journey, some lessons we learned there when creating these data sets with automatic annotations. Where is the emphasis? Not in capturing the image, but in creating the automatic annotations. Be careful. Because, well, you can have all these issues, but you can also use all these methods to actually provide some metrics there. And yeah, I think with that I conclude. I thank our sponsors.
I'm going to introduce you then Rosana Souza Rodrigues. Rosana holds a degree in medicine from the Federal University of Rio de Janeiro with a medical residency in radiology at the Clementino Fraga Filho University Hospital of the Federal University of Rio de Janeiro. She completed a master's degree and a PhD at the Federal University of Rio de Janeiro, including a period of internship at the University of Utah, and complete a postdoctorate in molecular imaging at the University of Pittsburgh. Currently, she teaches in the postgraduate program in radiology at the Faculty of Medicine of the Federal University of Rio de Janeiro and in the PhD of Medical Sciences. At the Door Institute for Research and Education, she also coordinates research in imaging and artificial intelligence. She coordinates the Research, Innovation, and Artificial Intelligence Laboratory in the Radiology and Diagnostic Imaging at the Clementino Fraga Filho University Hospital. Her area of expertise is thoracic radiology with an emphasis of molecular imaging, pulmonary inflammation, and medical image processing. Thank you very much.
So many information. I don't know where Federico finds so many information. Thank you very much for the kind introduction. Good morning. It's a pleasure to be here. So I will share with you some of our experience in developing an AI tool for lung evaluation. As Federico told you, I'm a radiologist, a chest radiologist, and I should say here. And so computed tomography is a key imaging method to analyze the lungs, and it's use X-rays to create cross-sectional images of the body. Only the U.S. It's not work. So only in the U.S., more than 20 million chest CT scans are performed each year, and our institution, IDOR, is linked to a huge hospital network in Brazil that perform almost 1 million chest CTs each year. And the number of CTs is increasing every year, and the number of radiologists are decreasing. So to develop AI tools, AI solution to help to assist radiologists to interpret these images is very important. So I was very attached to the title of the round session, and so I show you a very superficial pipeline of the development of an AI solution. So we start converting DICOM, it is the most common medical image format, to NIFT. NIFT is lighter, is easier to handle, and it's compatible with machine learning libraries. So we convert CT images into this NI format. And so it's a digital image that is a matrix of numbers where each number corresponds to 1 pixel. And in CT, each value represents the X-ray attenuation that represents the density of the tissue. So since it's a matrix of number, we need a mathematical model to analyze it. There are several mathematical models. We use neural networks to process the images. Neural network is a mathematical model that is inspired by the way the brain works. It's made of connected layers of neurons. The input layer receives the matrix of numbers, applies, like Enzo showed you, weights and bias to input data and produce. It process the data and pass to another layer and analyze the like edge, like several characters, like edges and textures, for example. I think that's too much information. Enzo showed you a lot of things about segmentation. That it's his work. It's the segmentation. Delineate the region that we're going to be analyzing, processed for the AI solutions. Our region of interest are the lungs and the lesions in the lungs. And after the segmentation, as Enzo showed you, we analyze these masks to detect, classify, and quantify several different pulmonary patterns, that's our case, and correlate it with function and clinical outcomes. We have at DOR a research group that is dedicated to develop AI tools for lung images, and we have different studies in different diseases like COPD, emphysema, some in COVID, and I don't know, sclerosis systemic, and et cetera, et cetera. And these studies led to development of AI solution that received the approval of Anvisa, that is the Brazilian regulatory agency. And it took us almost 2 years to go through all the steps and the regulatory steps to get the authorization and registration of this and this tool. Nowadays, we are integrating this tool to our PACS system. The PACS is the systems that radiologists see the images and make the report about the exams. And so we are implanting in one hospital. The images from the CT go to the hospital PACS and go to a server to be processed, and it generates one report that's sent back to the radiologist. And in this report, you can see several patterns like ground glass opacity, consolidation, emphysema, cyst, several different kinds of patterns that together make us define the disease, and it's very important mainly to the quantification, because of course quantification is a very, very important data to predict the severity of the disease. And so from this simple pipeline, we get to the integration of the tool, the solution in the clinical systems. It's very important to arrive here, because we know there is a big gap in AI, too many solutions that are developed that don't arrive in the clinical for the radiologists to use it, to be integrated with our system to help us to analyze the exams. And so this is our team. You have AI specialist, biomedical engineering, a guy that's a specialist in informatic imaging, and Bruno and I are radiologists, and you have the luck to have Alison with us. He's also a radiologist, but he has a background in biomedical imaging, and he bridged the gap between the developers and us. They translate what we need for what they can help us to develop. So that's it. Thank you very much.
Thank you, Rosana. And I invite Andrea, Enzo, and Rosana to stay here. And we have time for questions now. Questions? Come on. You see an amazing pipeline of everything, from data acquisition, data analyzing. Okay, and how to put that information on the clinic.
Hi, thank you for your presentation. This question is for Rosana. So I was very interested that you were able to modify the PACS systems. So the PACS you modify is from a vendor, is something from the hospital? Because it's not easy to modify a PACS.
No, it's a PACS of hospital. So we send it works in the intranet hospital. So it went to the server, that's intra-hospital server, process, and come back to the PACS. So when I receive a chest CT to analyze, I send it to the server. It's processing while I'm making my report, analyze the images and make a report. And when I'm in the middle of the process, like 1 minute, 2 minutes, it come back that report, automatic report. So I use because it is, I can use because it is approved. And so what I most use is the quantification, the volume, the extension of the disease. And so that's it. We are, nowadays we are putting we print the report, the automatic report together with my report and to send to the patient. And it's very important for the pneumologists, they use it a lot. For example, emphysema or interstitial disease, a patient, they repeat the chest chest CTs each year. And so you need to decide if it's increasing, like the infiltrates, that's very, very fine structures, very, sometimes is more extensive, but sometimes is really mild. And you need, if it's worse from 1 year to another one, it's necessary to start the medication. And it's very hard to decide by just seeing the images, and so it's I think that helps a lot this solution.
Okay, thanks.
Yeah, just if I can complement a little bit. So I think you asked if the PACS system was also developed in-house or if it's it's from a company. Is that what? So
this about the PACS, no?
Yeah, I think so. So
Fernanda can answer.
No, you can.
No, answer, please.
Yeah,
please.
no, because actually this is a PACS system that was developed in-house since 2000 even. Yeah, 2000. So the one hospital was the first digital hospital in Latin America. This is Quintador, and the same guy, so Conrado, that was there, Ivanei. So they developed this PACS that now is running in the 70 hospitals. So that's why it's more easily to implement any new framework and all the things. But Ivanei actually is the guy that can explain more about that. Yeah.
Thanks for your talk. Enzo, do you think that we can use your system for X-ray to use it for unsupervised segmentation in microscopy images, like cells, maybe?
You mean the segmentation model?
Yes.
Or for detecting or for controlling the quality of the segmentations?
No, for segmentation.
For segmentation, yeah, that could be used. Like it's a deep learning model. We work a lot on creating new architectures, like new. So it's not a basic like a standard unit. It's something different that we did there. For cell, that could work. Yeah, totally. So we can then discuss that if you want, but could be adapted.
Yes, because sometimes we have the same problem for people that need to segmentate a lot of images and a lot of cells, and then you have to make by your own.
Yeah.
Thank you.
Great.
Yeah, actually, I had the same question, but I did not get from your talk how that worked. If you don't have the ground truth, if you don't have the ground truth for a region, how could you estimate
that
quality?
Yeah.
And what is the ground truth if sometimes experts disagree among themselves?
Yeah, totally. So, I didn't have time to present that. That's a method called reverse classification accuracy, which is basically the idea is you have a reference data set of similar images for which you have ground truth. Okay, for those you have, but they may be the same you used to train your model. Now, in a new data set, you want to segment, and yeah, you have something to say to that?
No, just finish.
Okay. So in a new data set, you segment your images. Now, these images that you segmented in the new data set are the ones you want to estimate the quality. You want to estimate, in this case, the dice coefficient. That is what we use. So what you do is you train a reverse classifier. And what I mean by that is basically you use the information you predicted to train a model, and I will do like this because it's not actually trained. in this case, it's something else, but we can go into the details after that. And then you use that model that was trained on the predictions for segmenting the images for which you have ground truth. So you can compute the quality of those segmentations you did there. And the hypothesis is that if your segmentations were good, then they should be useful to train a model that is actually good at segmenting. And that's the way, when you estimate the quality of the segmentations back here, is when you use that number, and that number is highly correlated with the original number that you would get. That's the idea, a little bit.
Okay, I sort of get the idea. For medical imaging with standard X-ray, CT, or whatever procedure sounds fair. But when biomedical imaging with different conditions, different microscopes, different staining and acquisition quality comes into the game, we are probably lost.
We have the same issues in macroscopic images as well. We also have domain shifts between hospitals, between machines. These can be somehow harmonized. Now, it's true that it's a different domain. Here, what I showed is for anatomical segmentation, so organs, which are very regular, and that's what we take advantage of. But we have a paper now with us under revision where we did that for cells as well, with another technology that is in context learning, something different, but the same idea. And that worked much better for these cases. So there are things you can try to do. Not sure if it's going to work, but at least to have it, yeah.
It's a general question because Enzo talks about asking for license. I wanted to know how aware are the patients that their data are sharing and how this is managed in each of the cases. How well we know that our data, my RX, all of us are going to have RX in the, and are managed by platforms like Google or whatever to do different investigation.
Yeah, at least in our case, in our experience, that is clearly explained during the whole process. So we tell, in this case, the pregnant women that how we're going to use the data, how we are going to collect the data, and this all described in the consent that they're going to provide. So we have to commit to that, and we are going to use the data. If we're going to use for training, we're only going to use it for training, but we are not going to put it available. So that's how we do it.
For our case, we were working with publicly available datasets. Someone before us took care of that stage. Now, how that happened, I'm not sure. What I can tell is that many of them, sometimes, especially for these large-scale datasets, that were not really acquired for that purpose, were images that were already in the hospital. So what you usually get is a waiver from the board of the institutional board, telling, yeah, you can use it for research, and if you get that waiver, you can kind of go and go with that. Images have to be anonymized, but maybe many of the people that ended up in those datasets we use were not aware at the beginning that they were going to be used for that, and that's completely true.
Okay, we have a lot of questions from the audience, but we have run out of time. So let's thank again the speakers, and remember we have time for in the lunch time for talk with them. And thank you very much to you.